So I gave the overview of kind of things that have been going on in the RISC-V world in general. Today I'm talking about the lowRISC project, which of course has presented at ORConf for the last few years. To give a very brief overview of what we're about for anybody who hasn't seen a previous presentation, lowRISC is a not-for-profit project which aims to produce a Linux-capable open source system on chip. We build upon the RISC-V instruction set architecture, as well as open source implementations of RISC-V, including the Rocket implementation from Berkeley and the Pulpino implementation from ETH Zurich, as well as pulling in other pieces of IP and making other modifications on top of that. I guess two of our kind of key focuses are both flexibility and security. So I'll talk about, particularly with regards to our latest release, how we're kind of addressing those concerns. And our kind of aim is to, for us, it's about not just releasing the end thing, throwing it over the wall with an open source license, but to do it all out in the open as much as possible, in having the development process be as open as possible, having all of the associated tooling, scripts, benchmarks, verification, everything that we have in that direction is out there. There's nothing that's kind of held back. Now, of course, we perhaps want more of all those things I've just talked about, but it's not that there's anything that we're keeping secret. And so the lowRISC project itself is currently kind of based at the University of Cambridge, and at the kind of co-located there is the lowRISC CIC, the not-for-profit that I co-founded and worked for to support the project. And it comes out of our previous experience with the Raspberry Pi project, where I was kind of the volunteer #1, and my fellow lowRISC co-founder was also a co-founder of Raspberry Pi. And that kind of gave us the, I guess, the experience of what the power of a community can do, particularly a community who's interested in openness on kind of enacting change. So the lowRISC platform itself, so I mentioned, the aim is to produce this open source Linux-capable SoC, so 64-bit, multi-core, able to run Linux well, but kind of beyond that, we're interested in looking at how to move beyond the status quo, beyond what a current shipping SoC offers, or at least offers a slightly different take on that. So for us, the way we've been pursuing that are two things which you've probably heard me talk about before. One being minion cores, which are these small microcontroller class cores we use building on ETH's Pulpino work, which we use for I/O. And essentially the reasoning there is that, as I say, simple cores are essentially free in terms of area on a modern process, whereas tape outs are expensive, either due to making a mistake or because that your design wasn't as flexible as you needed it to be. And so, for us, it's very useful to try and offload as much, or try and implement as much of the chip that we can. So, say low-speed I/O, I think, is a good target for that. On using something that's reprogrammable, something that can be customized post-design time, and that's also something that's interesting to, say, a wider community once we have shipping hardware. As that gives you some ability to customize the chip that you have, whereas obviously the other route is to make modifications, send them back, and then wait for the next tape out in the next couple of years. The other thing we've been looking at is tag memory, which has a number of potential uses. For our main focus is security, as that's a very important aspect for us. I think so. I guess we'll go through that a little bit more in the diagrams on the coming slides, but the basic idea is that for every word in memory, you have a small amount of extra metadata associated with it. It's not a particularly new idea. Other architectures going way back to the 1960s have also had tag memory. It's kind of had a bit of a resurgence in recent years, and one of the advantages is that it allows you to, you might, for instance, have access control metadata with a word in memory. In the most trivial case, you might want to prevent a return address from being overwritten on your stack. and that's something which is very easy to do once you have this fine-grained metadata. And so most recently, if the people who've been following us, we kind of have a series, that our release process is kind of going to become more regular, hopefully from the next release onwards. But so far it's been mostly feature-based, so we get to a certain point where we did a certain target, and then we put it out there with documentation and tutorials. The most recent release, which we call 0.4, a couple of months ago, adds in, kind of builds on what we've had before. So I guess it probably makes sense to give a quick overview of the current SOC architecture. So we have a number of rocket cores, however many you choose to instantiate. Normally you choose to, I mean, if you're targeting our standard development board for Nexus 4 DDR, then you'd only really have space to instantiate one. So these are 64-bit cores with a small L1 cache and then an optional L2 configurable at design time. So this is the rocket core, and this part of the design is a modified version of the rocket chip generator, originally from UC Berkeley. We also have, so this is the Minion subsystem I was talking about. So in the most recent release, this provides it kind of acts as an intermediary between a number of different I/O devices. So we have added support for keyboard and screen, so that it's kind of nice. You can plug it in and it acts a bit like a real computer that's a bit sluggish. SD card, we moved away from using the SPI Xilinx IP and have now actually support the 4-bit SD protocol, which is gives us like speed improvement for us, and GPIO obviously. And so the Minion subsystem is hooked up via an AXI bus. So this part is all written in System Verilog, and this is building on top of the Pulpino work. And we've kind of we've done quite a lot of, we try very hard to make it so that it's easy for people to come along and insert their own IP into the design without having to understand or learn Chisel, in that we have a well-defined kind of entry points for how to, and documentation on how to go and add your own peripheral to the SoC. And of course, this part being Chisel and Tarlink. The other parts you see, these blue shaded boxes, these are the kind of the modification, well, representing the modifications needed to support tag memory. So I say we're going to associate some extra metadata with every word in memory. So logically, that means that we have to actually store that metadata somewhere. So there's just we kind of logically partition the external DRAM so that there's a separate portion of that for those 2 to 4 bits of extra metadata per word. And then we kind of hide this to the rest of the system through a tag cache, which will kind of, you can view this as being logically interposed between your external DRAM interface and your last level cache. And it basically produces something so that it's as if you're getting, say, 68 bits of data in at a time, with those last 4 bits being the tags that are stuffed in. The purpose of a tag cache being to mean that in the common case, you don't have to have 2 memory accesses for every last level cache miss, because that you can most frequently hit here. And that's actually something that we've been improved in the most recent release, which I'll talk about shortly. Yeah, I think we've kind of covered most of this. We started to look more at potential use cases and compiler modifications to support those use cases. The majority of them are security oriented, but then there are more general profiling or debugging based workload potential uses. I mean, a very straightforward use of tag memory is just use it for infinite memory watch points rather than just having a kind of fixed set that your hardware supports. And so, of course, that can be useful for building all sorts of performance or profiling tools, potentially using a separate software-managed shadow memory. And so previously, I've talked about tag memory, and it's kind of been there, and you've been able to do some simple demonstrations. What we've done in the most recent release is to actually try and pin down what the interface is between how you actually control that, so how you specify rules which are then enforced by the hardware, how to make sure that this isn't actually a complex or costly thing to add to your chip. I mean, we looked at a number of different approaches to doing this. I mean, fundamentally what we're trying to do is you're saying, we have this ability to associate extra metadata with every word in memory, which also gets propagated through to registers once you load and store things. But then how do you interpret that? How do I decide that when I access this memory location, whether it should be an exception, whether that should propagate, how much flexibility do you have? And there's actually quite a range of trade-offs you can make here. Different systems have looked at schemes of differing levels of complexity. We've actually kind of picked something out which gives you the ability to implement basically these sorts of use cases without any real problems, with some software cooperation, without requiring kind of complex additional hardware. What we wanted to avoid was having to have associative lookups to look up what the rule is for this particular combination of input tags. So instead we have something that's very simple, and there are kind of different ways of this is one way of kind of drawing how it works. I like to think of it as being almost like you have a separate tag pipeline. So we have your instruction comes in, and it goes through your standard, let's say the integer ALU, it's an add, but then you also map this to a tag instruction, say for us we have say add, or all of the kind of ALU instructions would map to a kind of tag ALU instruction. And in order to control what happens, we just have a small number of configurable masks. So this is just controlled by a control register. So let's say I have the example of I want to, when I access a certain location in memory, I want to see it so that I want that to act as a watch point, so I want an exception. All that happens is that I set the appropriate mask here, so the tag check mask. So I set that so that, let's say that tag is tag 10, for instance. I set the mask so that, it is so that the second bit in the tag is set. I set that mask so that whenever that happens, we'll have an exception. So that actually provides a lot of control with a very small, a trivial amount of additional states, and we also have masks that control propagation. So essentially, for any individual tag, you control whether it traps on an ALU instruction or a load instruction or a store instruction, and they're kind of controlled independently for different tags. So there are some use cases where you might want to do slightly more complex checks, which wouldn't be supported, but it actually gets you quite a long way with a kind of trivial amount of hardware. And we also have the reason we wanted to start out with this simple scheme is that it's actually quite easy to extend this to support something more complex, perhaps something that involves a associative lookup or a cache-based lookup, in that you can just kind of you can add in almost a kind of, I like to think of it as a secondary tag pipeline, which is enabled or disabled on a per process basis. And I guess on a similar theme, we're looking to try and minimize the overhead for applications that either make minimal use of tags or make no use of tags at all. And so we added in this support for that allows software to control how tags are interpreted and how they act. We then wanted to look at minimizing the cost to software. So you remember we had this tag cache here. So let's say you have your L2 cache at 128 kilobytes. You might have a tag cache of 16, 32, 64 kilobytes. As you increase the size of your tag cache, you reduce the potential additional misses. But we can actually be a little bit smarter than that, because we can observe that actually in many cases, particularly for these sort of policies where we're protecting, say, code pointers, or it's only on, so if you're tagging certain instructions in memory, that's only ever going to be on code pages, so a relatively small region of memory. There's actually a huge amount of sparsity, and we can exploit that because that's easy. So we implement a hierarchical scheme which is logically very simple, where you can you have a for each cache line worth of words, you can indicate recognize whether that has no tag set at all, and then you have another hierarchy that has another level in the hierarchy that marks for a cache line worth of of a previous level down, whether any tags are present. And so through that approach, you can have, so you could have a single bit indicating that, say, the entire page has no tags at all. And so this takes up a trivial amount of space in your tag cache, meaning that if you have this sort of sparsity in your workload, you have much higher reach. You can get away with a potentially much smaller tag cache, and certainly because of it, you end up with kind of almost no lookups for any workload that has no use of tags whatsoever. You're not actually adding in any additional overhead over the kind of small additional hardware cost. And so Wei wrote some extensive documentation on this on our website. There's a RISC-V workshop presentation from China earlier this year that goes into much more detail. And there's a paper at ICCD that has kind of a performance study that we did with some of our colleagues at Computer Lab in Cambridge. And and we also had a summer student who worked with us to look at adding software support for all the things I've been talking about. So adding support for Linux kernel for context switch, for making sure that your tags on your general purpose registers are transferred correctly and without triggering unexpected exceptions, that the implementation of tags works well with virtual memory, with paging off to disk, the ability to kind of embed tags as metadata in ELF binaries, which you might want to do for tagging code. So all of these things did a really great job. So there's kind of a detailed write-up that you can look out for in the next couple of weeks. I've been doing lots of work recently, if you've been following, on the RISC-V mailing list on RISC-V LLVM. So we're leading the effort on upstreaming and implementing a high-quality RISC-V LLVM backend. We currently have the vast majority of the GCC torture suite passing for RV32i. The kind of plan is basically to build it up piece by piece. We have this nice, the nice property of the RISC-V ISA that you can start with a very minimal base and then add on extra extensions. So it feels like a nice way to build a compiler as well. We start with a minimal base that's enough to compile with whatever you want, get that totally bulletproof, and then it's very easy to add on the additional extensions. So currently the code output is not particularly well optimized. That hasn't been a focus so far. Over the coming months, I'll be focusing on improving the generated code quality, adding support for the MAFD extensions. It's likely we'll get RV64 support by the end of the year as well. If your employer is interested in RISC-V LLVM, or you have an interest, I would love more assistance in terms of engineering time, or if your employer is interested in sponsoring our work, that could be that could work out well. I'm also have a Birds of a Feather session at the LLVM dev meeting next month, which, again, if your employer is interested in RISC-V LLVM, that could be a good event to attend. There are a number of people or different groups who have ended up with different implementations of RISC-V backends from different sources, which is non-ideal, and the hope is that we will all get together and sort of work out how to best merge our efforts and move things forward as best as possible. I'll skip that. And we've also had a very successful year in terms of Google Summer of Code projects, which I'll step through somewhat quickly. We had a great project this year from Nikitas. He was motivated by CubeSat. So he'd been working on a number of CubeSat projects before on the software side. He'd done a few digital design courses as an undergraduate and in his master's course, and wanted to try and apply that to make it possible to have a open source hardware in these, or an open source CPU design in these CubeSat launches. And one of the requirements of that is some degree of fault tolerance. So he was looking at implementing core lockstep on top of a Minion subsystem. And he did a really great job in that he managed to both implement a really nice prototype of core lockstep and how that works, but also made really useful contributions to the Minion subsystem in general. He got it working on Verilator, did some useful code cleanups, added extra documentation, got it working on the RT in a nice standalone configuration, has kind of prototyped a code generation system for configuring it. So it's that's worked out really well. You can kind of see the work on GitHub currently, and again, as with all of these GSOC projects, there are blog posts queued up over the next couple of weeks. We had another project looking at, with more of an educational focus. So it's a tool that's quite frequently used in undergraduate classes and universities is Mars, which is basically a MIPS simulator in IDE. It has a nice view of, you can see the currently set registers, the state of the stack. It has support for doing things that help with programming exercises, sort of tracking branch predictor state and those sorts of things. He's ported that from MIPS to RISC-V, and we've imaginatively called it RAS. Believe it or not, we did actually brainstorm names, but we kind of, yeah, that was the best we came up with. We've also had really interesting work looking at supporting oblivious RAM, which is basically it's attempting to obfuscate external memory accesses, so the access type and the address. And of course, to do that, you need to introduce all sorts of additional memory accesses. So you can imagine the overhead is really quite high, so it's quite a niche sort of, I mean, it's something you probably only use if you have very, very high requirements to try and prevent your external bus access or reduce the amount of information that people can gain by snooping your external buses. But Yeonju did a great job of prototyping that in Spike, produced an initial Verilog implementation. We also had a port of the CMSys DSP library, which ARM provide for the Cortex M0 under a nice BSD license, and so we thought, oh, it would be interesting to port that to Pulpino and the DSP extensions there. So Mustafa kind of worked through, and it looks like we mostly does pretty well so far. In terms of development priorities, the next step for hardware development for lowRISC is moving to the latest upstream rocket. It's been a while since we've updated to upstream rocket. As if you've been following development there, things have changed quite rapidly since Sci-Fi spun out of Berkeley. They've been doing lots of really great, interesting work, but it's also involved disruptive changes and kind of redesigns of very large portions of a chip, and particularly to try and maintain the properties I was talking about, as in making it easy to add in system Verilog IP. That needs quite a lot of reworking to unpick that and add our stuff back in and so on. So it's a fiddly process, but I think we're making reasonable progress there. As the LVM work I talked about, Jonathan Kimmett's been doing work on integrating open source Ethernet IP as an alternative to some of the Xilinx IP that's been used previously. And of course, further developments along the lines of the minion cores and tag memory I've been talking about. If you're interested in getting involved, like our next speaker is a very interesting project building on top of lowRISC. There's a whole bunch of interesting things like that that people like yourselves might want to get involved in. Feel free to chat to me or drop by our mailing list, check GitHub for open issues. We're always welcoming to new contributors, happy to set up a phone call, try and help you out if you're getting stuck anywhere. We've just put out a job advert. We're hiring for a new kind of SOC or security-focused hardware design engineer. So please pass that on to anybody you think might be looking, or have a look yourselves. So I now work full-time under lowRISC CIC, which is the not-for-profit that we co-founded. As we're certainly with the work I'm doing, it's focused more on development rather than research, as would make more sense under the university. So we're, so the LLVM work I'm currently doing is funded by a external party who wants to see RISC-V LLVM develop, and there's some funding for the coming months of that at least. If you're interested in supporting work such as RISC-V LLVM or some of the things I'm talking about, then we're very open to consultancy work that kind of aligns with the sort of directions that I've been discussing. And of course, being a not-for-profit, everything that we bring in that way just goes back to supporting the community work and the, our overall project goals. And I think that's the end of the presentation. So it's, I'm very grateful to everybody who's been working on the project so far. Unfortunately, most of the rest of the lowRISC team are either traveling elsewhere or just getting back from places and aren't here. It's good I can have a presentation that's talking mostly about work that other people have done. We can always find out much more information on our website, particularly the documentation and tutorials, and I'll happily take any questions. Graham.
So from the software developer's perspective, what does the tag memory look like? Like, what do you see on the software side?
Yeah, so, well, in terms of the interface, we've kind of pinned down the ISA interface, exactly how it looks to your standard programmer is kind of still in discussion. For our take on tag memory is that most of the security-oriented things we're talking about are compiler support or require compiler support. So some tag memory systems, they try and completely isolate your tags from the code that's running, which offers you high degrees of security but tends to be much more complex to support. Whereas we're looking at it as something like stack smashing protection that you'd get in GCC or Clang, where it's not going to help you for if you're just downloading software from random sources, but it's a useful kind of hardening that you can, a hardening option that you have to enhance security on your software. So it mostly looks like manipulations of this tag control register. So if you say that you want to protect your return address on the stack, you might manipulate the tag control register to allow you to for that time when you actually do want to clear it from a stack, you manipulate tag control to allow that, and then put it back again. Yep. We have a. Oh, sorry.
Cheers. Yeah, I was just wondering why you chose to only have 2 bits for the tags, because potentially that's something that could be really useful for all manner of applications, and actually I can quite easily see 2 bits just being consumed by operating system stuff.
Yeah,
and
so it's a design time configurable. So actually in our standard configuration, there are 4 bits currently. It's not particularly pinned down exactly how many you'd have. I mean, as you increase the number of tags, then the overhead of extending your L1 and L2 caches and the size that you need for your tag cache will increase. So it's something that perhaps people would customize on a kind of per design basis. I think we're hoping that there'll be an obvious sweet spot for, as you say, just about enough for 1 or 2 standard use cases, plus leaving a little bit of room for something that's application specific, which is hopefully 2 to 4 bits. But we don't really have evidence to support that currently. But it seems like that you can do useful things with that.
Debug. So you've got 2 forms of RISC-V processor in the chip. You've got the Polpino and the Rocket.
Yep.
Do they share the same debug infrastructure? What's going on there?
So no, not currently. Rocket is hooked up to OpenSOC debug, and the version of Rocket we have doesn't implement, I don't think, any version of the RISC-V debug spec. So that's, again, another one of the long list of motivations to move to a newer Rocket. There's kind of all sorts of things like this, the latest version of privilege spec, which will be the benefit of going through that pain of moving to the latest Rocket. Hooking up Polpino to the trace debug infrastructure and ensuring that Polpino run control debug works, which I think there is some support for, but we haven't really tested ourselves. They're to-do tasks.
So I'm going to be running a workshop on just open source hardware later this year.
Mm-hmm.
And one of my thoughts was to use lowRISC.
Yep.
So is it at the stage where I could build it relatively easily, compile it for an FPGA, download some cool software and boot Linux and do something? It would be a pretty cool thing to boot Linux and then have people write a driver or something that can drive the minions. Is it at that level yet where you can kind of do that sort of work with it?
I think it's doable for that. I think the debug experience could be improved, and I suppose for that sort of thing there might be a advantage to having a smaller design for faster synthesis times. I mean, one of we should follow up offline, as Jonathan did some interesting work on using a RT tethered to your host system, and then having a QEMU running a RISC-V kernel and then communicating with a device on your RT, which is a little bit convoluted, but actually gives you a really nice way of kind of rapidly iterating on both the driver side and the FPGA side. But yeah, we'll chat about it.
Hi. I remember when lowRISC started off, there was quite an aggressive schedule to fab something out. How's that going on?
Yeah, so I think the most likely route of getting a chip fabbed will probably be partnering with a company who's kind of adapting or building on top of the lowRISC platform. So we don't have anything to announce currently, but we're kind of working towards that goal.
Cool.
And I think that's it.
I could ask one more question.
Okay, I'll allow
I
it.
think a while back we chatted about minion cores and higher bandwidth I/O. Did any more research go along those lines, or is that still a?
It's not something we spend much time on. I think that with the Ethernet work that Jonathan's been doing, here we're interested in looking at which parts you could easily offload to a minion core and what the kind of exactly how that split might work, but there hasn't been other developments. So.
That sounds interesting. Thank you.
Great. Thanks very much.